Okay, chapter 15 deals with chemical kinetics. In my opinion, probably the most difficult chapter in all of general chemistry. So, I've actually done this myself. So, at least in my shower, I one time got some geckos, and I remember, interestingly enough, I was teaching this, and this is my introduction as well for this chapter. And oh, if you cool lizards down, they're slower. And I had some geckos in my shower, and if you capture a gecko, one of the things that's kind of tragic. Well, it's not tragic. They lose their tails, and I always feel kind of bad whenever I capture geckos and they drop their tails. I'm like, okay, is there a way I can get this gecko out of my shower, and also not have to, have it lose its tail? And so I found the gecko was in the shower, and I dumped a bunch of cold water in the shower, and the gecko, of course, was initially a little shocked, and it was running around, and it got slower and slower and slower, and then it stopped moving. So then I can easily go and pick it up and take it outside. Gecko kept his tail. So funny enough, you can apply this. So I'm proof to this. So, but this chapter studies chemical kinetics. This is the speed of reaction. So temperature is one of the major effects of the things that affect chemical reactions. So the speed of chemical reaction is known as its reaction rate, and the rate of reaction is how fast things are going, how much products are being generated or reactants are being consumed. And it's very important that we can control the speed of chemical reactions. This is because we make stuff, and knowing how to control chemical reactions, have chemical reactions happen that we want to happen, prevent reactions that we don't want to happen, not to happen. This is all very important for our industry. And rate is how much is changed. So for speed is an example of something as a rate. So speed is miles, and distance. Speed is change in distance over change in time. So in this case, distance over time, miles per hour. That's what we're familiar with driving our car, at least. So concentration, though, and reaction rates, it's change in concentration over change in time. So it's change in molar over change in time. And so if you look at this reaction here, hydrogen plus iodine makes 2 hydrogen iodides. The rate, or the rate of disappearance of hydrogen, so if you look at this, the rate of disappearance of hydrogen is a change in hydrogen over change in time, or the change of hydrogen at some later time minus the initial time divided by the difference in the times. And I know calculus often is not a part of the prerequisites for this class, but if you recognize this, this is really just a derivative. So it's a calculus derivative, and it's the rate. So for instance, here you can see the reaction rate. You have products going to reactants. I'm sorry. Reactants going to products, excuse me. And you see over time, eventually all the reactants are consumed, and then products are formed. And that's with a moderate rate. And the bottom here, you have reaction with a slow rate, so just slowly over time. So it's some reactions are fast, some reactions are slow. This is not surprising. So, and they vary with temperature and concentration. We'll talk about that later. So if you look at this chart, the y-axis is concentration, the x-axis is time. And if you notice here, this is looking at the hydrogen plus iodine makes 2 hydrogen iodides. So over time, the concentration of hydrogen is decreasing, while the concentration of the product hydrogen iodide is increasing. So reactants gets consumed, so their rate is negative, at least they're being depleted, and then the products, it's positive direction, concentration is increasing. So with these reactants, and the rate, as I said before, is a change of concentration over change in time. In this case, well, it's negative for hydrogen because it's disappearing. It's the reactant. So the average rate is just looking at the measured concentrations over any particular time period. And so it's also the slope of the tangent of the curve, so linear approximation of a curve. Well, That's the I guess the instantaneous rate is the slope of the tangent. The If you look over a long period of time, that's the average rate. And so if you look at smaller time intervals, you get closer to the instantaneous rate. And again, this is a calculus derivative concept. So here, this chart shows the average rate of reaction at different times, and you can see that the rate is changing and the time change, and this is always 10 seconds. So the instantaneous rate, it's the slope of the tangent at the curve, and it's the derivative. So for all the calculus fans, yay calculus fans. And the reaction rate does change over time. This is one of the things that makes this chapter difficult, among other things. The rate tends to slow because the concentrations decrease. And at some point in time, the reaction stops, either because something's been consumed or the reaction reaches equilibrium. And equilibrium we'll talk about much more next chapter. So reaction rate in stoichiometry. So this is important for the rates in terms of the ratios and the reactions. So this is easy for, well, it's 1 to 1 to 2. So every 1 mole of hydrogen and 1 mole of iodine that's consumed, 2 moles of hydrogen iodide are generated. And then if you have the overall reaction rate, this is the change in concentration is multiplied by 1 divided by the coefficient. So it's not that, and for hydrogen iodide, you think it would change by 1/2, 1 over that. It actually doubles. So for every 1 mole of hydrogen consumed, 2 moles of hydrogen iodide are generated. So that's a little misunderstanding. A little. That's the overall with that equation on there. That's a very common error in terms of what students make. So again, we have this chart here, the concentration on the y-axis, time on the x-axis, and you have it for the product hydrogen iodide in red on the top and green hydrogen on the bottom, rate of disappearance of hydrogen. So the instantaneous rate let's see, using hydrogen, instantaneous rate is, so you're calculating the rate in 2 different times, but you have to divide the rate by 2 because of the hydrogen iodide. So this one works for the overall reaction rate. So it's the amount of going forward. But when you look at each individual species, don't forget to multiply the hydrogen iodide by 2. So that's what those previous equations relate to, was the overall chemical reaction. So you have to measure it. You have to measure so components and many points in time. So there's many ways to do these. So very commonly you can use, spectroscopy is very common, polarimetry, so it draws things off, and pressure. So spectroscopy is one of the easiest ones because you're not changing anything. Nothing is changing. Pressure, of course, only works if the reaction increases or decreases pressure. So polarimetry measures the change degree of the, okay, well, you can read this yourself, I suppose. So so that's one ways you can measure the reactions. So you can take samples as well, and then these are 2 ways. Aliquots can be taken off, and then analyzing them, and also gas chromatography. This separates things out by terms of volatility. And so here is an example of one. This would be spectrometer, using a spectrometer. And here's another one, an aliquot, to look at various things. So what factors affect the reaction rates? So it depends on one or more things, and the rate law describes the overall chemical reaction. And the generic rate law, and we're using the generic term A, the rate is some rate constant times the concentration. So those brackets, those solid brackets, means concentration in moles per liter raised to some n power. And in this case, it says this integer. It actually can be it can be a fraction of two integers as well. So the reaction order, that's the number of that exponent. So and for this rate log, rate equals k NO2, and that should be squared on the top, and O2. That means that it's second order with respect to nitrogen monoxide and first order with respect to oxygen, and the overall reaction rate is the sum of the exponents, so it would be 2 plus 1 or 3. So if the reaction is zero order, the rate of reaction is always the same. Doubling the concentration of A will have absolutely no effect on the reaction rate. So an example of something like this oftentimes are phase changes. So the phase changes for a constant heat supply, this often is a zero order reaction, for instance. The reaction as first order is directly proportional to the reaction concentration. So doubling the concentration will double the rate of reaction. And almost everything, absolutely everything in the universe responds in a first order fashion. You can even make it, you can even force it to follow a first order kinetic reaction. So honestly, this is amazing. Absolutely everything follows this, and I'm emphasizing it. Nuclear decay follows this. Interest rates at banks follow this as well. So all these things is very, very consistent across almost everything in the universe is first order. And even if it's not first order, you can force it to be first order in a process we call pseudo first order. That's used quite a bit in biochemistry and biology. So, and I think it's amazing. So this is one of the things that as I studied and I thought about it more, like, wow. Especially when you study calculus and you go through and you learn that the integral of inverse x dx is natural log, and the natural log is what many times goes for this first order. The first order stuff is all natural log. We'll find out soon about that. That's just amazing that the entire universe more or less behaves in this fashion, and it's completely modeled perfectly by mathematics. So that is amazing to me. Okay, but back to chemistry. Some reactions are second order, and that means if you double the concentration, you quadruple the rate. So can you imagine a bank like that? So if you put in $100 and you had your rate, if you put in $200, you quadruple your rate of return. So that would be a great reaction. That would be a great bank for rich folks, right? But this is also how reactions can get out of hand as well. So you can see there's a drawback to this. So you can see here's some of the things, reaction rate over time. For the first chart here on the left, concentration of A is in the in the y-axis. The time is in the x-axis. So I'm sorry, the concentration of the reactants is in the y-axis, and the time is in the x-axis. And you can see zero order, it's a straight line. First order, it's a parabola. Second order is going to be a cubic. And then you look at the rate versus the reaction concentration. So calculus folks, this is derivative. Rate, or the first derivative, on the y-axis, and concentration on the x-axis. Zero order, you get a constant horizontal line. First order, you have a linear, and second order, you have a quadratic. So not surprising if you study calculus. So this particular reaction, A goes to products at doubling concentration. A causes the rate to double. What is the order of the reaction? That's first order. So determine the order of reaction. This is something that you have to find experimentally. Although most things are first order, things are not always first order. So, I mean, what would chemistry class be unless I had an exception to the rule? And so we're getting better at being able to predict reaction rate without experiments, but it's really hard. Which I'll explain later, because when molecules approach each other, they kind of dance around each other. So it's hard to predict how the chemical reaction is going to go just by looking at it. We really just have to do it experimentally, and we're still even now unable to do that, just by using simulation, for instance. So, and another way we can look at the chemical reaction rate is using integrated rate laws. So, of course, I know I keep on referring to calculus. So the integral of inverse x is natural log, and so first order natural logs are important. The integral of 1 over x squared dx is minus inverse x, so inverse x is important for second order reactions. So we can get integrated rate laws. So that's where these come from. It's a calculus concept. So first order, its rate is rate constant times the concentration of A to the first power. The integrated rate law is the natural log of concentration of A equals minus the rate constant times the time plus the natural log of the initial concentration. So you get that graph. And if you graph the natural log of, so if you graph natural log of concentration versus time, you get a straight line. It's first order. And this is the image of that right there. So that's one way you can decide the order of a reaction is by graphing the concentrations. And what about when there's multiple reactants? So you have to, well, you have to do different experiments. It's easiest when you hold one reaction constant or one reactant constant, but you can do substitution. It makes the math easier if you hold one reactant constant. But it's not necessarily needed. You just need the number of unknowns equal the number of equations that you have. So it depends on the number of unknowns you have and the number of equations you have. So if you have 3 unknowns, you have to have 3 independent equations to be able to solve that series of variables. So that's an algebra concept. So, and you have to do it from the experimental data. And the end result has a following form. The rate for 2 components is the rate constant times concentration of A raised to some exponent power m, concentration of B raised to some exponent n. The overall reaction order is the sum of the exponents. So second order reactions, so similar to first order, except you have the inverse of concentration equals positive kT plus 1 divided by the initial concentration. And why is this positive? Because the integral of 1 over x squared dx is minus inverse x. So for your calculus folks. So that's the reason why it's positive. And then you can have this on the half-life for this is 1 over, we'll cover some half-life concepts later. Half-life 1 over rate constant times initial concentration is the half-life. So here's the second order where you have the inverse of the concentration versus time is a slope. Zero order reactions, these are constant rates. The concentration of A is minus kT plus the concentration of the initial, and it's just a straight line going down. So there's not really necessarily a need for the integrated rate law, if you will. It's I guess to me it's kind of obvious. You're not really doing any calculus here. So it's just going. It's the integral of the rate. The rate is constant, and the antiderivative of a constant is just a line. A constant times the variable. Half-life. This is the time that it takes for half of the concentration to go away of a reactant. And this depends on the order of reaction. So in half-lives, you see this quite a bit in nuclear decay, for instance. And nuclear decay is first order, so the half-lives don't change. Second order, the half-lives change. So for instance, here, if you start off with 1 molar and the half-life is 100 seconds, after 100 seconds, you have half a molar. After 200 seconds, you have a quarter molar. And then it's an eighth. After 300, fourth would be 1/16 of a molar, and so on. So that's just plain old 1/2 raised to the power of n. So conceptual question here. These images show the first order reaction at various times. The black circles are the reactant A. What is the half-life for this reaction? So 2, 4, 6, 8. There are 10 circles. So when do we have reaches 5. Do I 5? Or am I counting that right? 2, 4, 6. Oh, yeah. So after there's 10 circles, and after 5 of them are consumed, that's at 90 seconds. So first order reaction has a half-life of 25 minutes. The initial concentration of A is 0.3 molar. What is the concentration after 50 minutes? So and so it's 2 half-lives. So 2 half-lives means it goes down by a factor of 4. What is half-life? So let's see, A to B. The concentration A, what is the concentration to B after 50 minutes? So the concentration of A goes down by half. So that means it becomes 0.15 molar, and then after another, so then it goes up by another half. That means it's going to be 0.75 molar. So if A then goes down to 0.75 molar, that means B has to have gone up then by 0.225 molar. So because it's a 1-to-1 concentration. This is also assuming that there's no B in the beginning. So here's a summary of the different integrated rate laws. So 0 order, 1st order, 2nd order, and what their integrated rate law looks like. In the half-life, if you're wondering the half-life for the 2nd order, it's just that's a natural log of 2. So that's a natural log of 2 over K. So that's all that is. So basic relationships, you have to determine the reaction order and rate law experimentally. We don't know how to do that even today. How to do that just without an experiment. And the rate law, this also relates the reaction to the concentration of the reactants. And the integrated rate law relates the concentrations to time, or the reactants to time. So the rate law is the rates, the integrated rate law is the antiderivative, so it's the concentration. So, and if you haven't taken calculus, I do apologize. I recommend you take calculus, of course. But you can know this. It's fine just to understand, or just to get these concepts, and if you really don't get them, just memorize them of sorts, and then know how to use the equations. But the concepts are calculus and base. In half-life, it's the amount of time it takes for half of the reactant to get to its half its value. And for first-order reactions, it's independent. So it's just the natural log of 2 divided by the rate constant. And the half-lives of 0 order and 2nd order, they depend on the initial concentrations. So we can determine the rate law for A going to product using graphs. So for instance, if you're looking at the concentration of A versus time, if the concentration of the reactant versus time is linear, it's 0 order. If it's the natural log of the concentration versus time is linear, then it's then it's 1st order. If it's the inverse versus time, it's 2nd order. So a decomposition reaction, which is able to slow down as the reaction proceeds, has a half-life that depends on the initial concentration of the reaction. Which statement is most likely true about the reaction is probably 2nd order. So because if it slows down, that means it's not 1st order. And if the half-life is not dependent on the initial concentration, the half-life depends on the initial concentration, then it's not 1st order. So it's most likely 2nd order. So the effect of temperature on the rates. So we have the Arrhenius equation. The rate constant K is equal to some frequency factor times E to the minus EA over RT. EA is the activation energy. So the pre-exponential frequency factor, this is the rate the reactant energy approaches approaches the activation energy. It really has to do with the type of collisions, molecular collisions, we'll learn later. Activation energy, this is the minimum energy needed to start the reaction. Why do you need energy to start the reaction? Because molecules and atoms have electron clouds around them, and electron clouds repel each other. So in order for a reaction to happen, electron clouds, regions of negative charge have to approach each other. and the regions of a negative charge have to be able to overcome a Coulombic barrier in order to interact. So that's the reason why activation energy is needed. And R is just the gas constant. So if you look here, on the y-axis you have energy, x-axis you have reaction progress. Reaction progress is usually an internuclear distance, like a hydrogen distance or hydrogen-oxygen distance. And as the reaction progresses, you can see that you start off with the reactants and higher potential energy than the products, but as they approach each other, so as the hydrogen and the oxygen approach each other, the potential energy goes up. Why is that? Because the negative electron clouds are repelling. Then they form a transition state, and then they react, and then they form products. So almost all chemical reactions have energy barriers. Some don't, but those tend to be rare. And it's because of the, like I said before, the interaction between the electron clouds. It needs energy to be able to go and deal with the repelling of the electron clouds. Activated complex, sometimes called a transition state. It's an in-between state. So it says it's no longer really the reactants, is no longer the products. It's in that in-between state. And these are at higher energy. So an example one here for methyl isonitrile to rearrange, there has to be a bond break and a new bond form. So of course, as this happens, it's going to take energy to happen. And you have the reactant going to the product, and then you have this transition state as the bonds are broken and it's moving around. So that's what we mean by this activated complex or the transition state. And the active energy, activation energy is the difference. Well, it's how much energy you have to put into the system for it to react. And then the frequency, it's the number of molecules that align at any given point in time. So this frequency factor, it's the number of things that get to this activation barrier per unit time. And it usually, this one is going to go on without, this reaction doesn't happens without a molecular collision, but they usually have to deal with molecular collisions. And this one here, it's unique because it's more about how the molecule vibrates. And the exponential factor of this equation, the Arrhenius equation, is typically a number between 0 and 1. It represents that. So this is the fraction of the reactant molecules that can make it over the energy barrier. So the higher this energy barrier, the harder it is to overcome it, which makes sense. The taller the wall, the harder it is to scale. So increasing temperature tends to increase the number of molecules that overcome the energy barrier. And I even use the word tens. So actually, you can have temperatures that for a chemical reaction is actually a range. So this is an advanced concept, but you can be too hot to react because if you have too much kinetic energy, then the collisions can be too elastic, and then no transition state can form. But that tends to be a rare thing. So, but the general rule is increasing temperature tends to increase the reaction rate for most of the time. So I always want you to explore more. So that's that's your teaser to it's more complicated. And hopefully you've seen this before, thermal energy distribution. So you look at the y-axis is the number of molecules, and the x-axis is energy. In this case, kinetic energy. Well, in terms of translational kinetic energy. And if there's an activation energy, generally speaking, at a higher temperature, there's going to be a higher fraction that reach that activation energy than at a lower temperature. And so if you look at certain reactions like burning, so paper burns, it's not surprisingly, but even at room temperature, paper is burning because a small fraction of molecules of air at room temperature have enough energy to engage in the chemical reaction. Whereas if you light a match to paper, it'll burn away in an instant. Oh, and it's in a couple seconds. So it goes to show you that that temperature can really speed up a chemical reaction that happens. So the frequency factor, it's the number of times that the reactants approach the activation barrier, especially in terms of effective collisions. The exponential factor, this is the number that of these attempts overcome the activation energy barrier. And this exponential factor increases with increasing temperature, but decreases with increasing activation energy. And that's just because of the ratio of the nature there and the fraction and the exponent. Which statement best explains why reaction rates generally increase with increasing temperature? It has to deal with the number of molecules that have enough energy to get over the activation energy. And of course, I mentioned before, an advanced topic is if you're too hot, then you actually the reaction rate can go down. But that's a more advanced concept, but I like talking about the exceptions to the rules. Oop, went too fast. The Arrhenius plot. So just like the other equations, exponential equations, you can go and you can take the natural log of them, and you've seen these equations pop up many times. And we have the equation of a line here, where the natural log of the race constant equals the slope minus activation energy over r times the inverse temperature plus the natural log of a, the frequency factor. And you can take the 2-point form and get rid of the natural log of a and have this form for the Arrhenius equation. Collision theory. So this is for in order for a reaction to take place, the molecules need to collide with each other. And once they collide, they may or may not react depending on a few factors. So the collision doesn't have energy to break the bonds and doesn't have enough activation energy. And these need to collide for the proper orientation for the new bonds to form. We do some simulations on this, and actually some of it's almost amazing the chemical reactions that ever take place, because the number of collisions that happen that are effective can oftentimes be very low. And many molecules, when they come to each other and they collide, they actually kind of dance around each other. They dance and they may form an activated complex or transition state, and maybe they form other ones, and sometimes they might dance for a bit and then fly apart. So it really depends. So the effective collisions, so there has to be enough energy in order for the chemical reaction to happen. It's to surmount that activation energy. So that's the one of them. And the frequency factor. So frequency factor is also the orientation of the molecules and the collision frequency. So certain collisions don't make reactions. So for instance here, if you look at this two NOCLs reacting to form 2 nitrogen monoxides plus chlorine gas, there has to be a specific type of collision. In this case, the chlorines have to have an effective collision. So in truth, the matter is when molecules are flying around, they often can kind of come close to each other, and they can dance, and then they can collide in the right way. So it is even more complicated than this. So, but it tends to be actually very few chemical reactions, or if the number of collisions that must occur for a reaction to happen actually very large. So the collisions that lead to reacting are called effective collisions. And the more effective collisions there are, the faster reaction rate. And if you haven't guessed, if the molecules are spherical, especially if they're atoms, if they're spherical atoms reacting with each other, then those tend to be the highest frequency factor, because every single collision is a potential effective collision. So, and the more collisions that happen, the faster the rate. So you can see this is what's going to affect the chemical reaction. So temperature is needed to overcome the barrier, plus temperature means things are moving faster. So faster moving means more collisions. Also concentration. We already know concentration. Concentration is important because if there's more stuff, there's more collisions, faster rate. So orientation factor. This is the frequency factor, related frequency factor to collision frequency. For most reactions, it's less than 1. The atoms colliding, it's about 1 because they're spheres. And some reactions can have a p greater than 1 in terms of electrons transfer. So you can have unexpectedly higher than you'd expect. So proper orientation is important. And again, this is more complicated because they actually can dance around each other, like I said. But for most reactions, orientation factor is much, much less than 1. It's really small, actually, really, really small. So which reaction do you expect to have the smallest orientation factor? So this is the one that has to have the collisions be the most specific, and well, it's at least specific. So it's the smallest orientation factor. These are atoms, so these are real easy to orient each other. So it's not going to matter really which side of the sphere you hit them on. Reaction mechanisms. So it's funny that the more that we know about something, the kind of more drawn out and prettier picture. We've gotten a lot better with this, but this was really proposed in like the middle 19th century, early 19th century maybe, how chemical reactions happen. And we've gotten better with this because we can do spectroscopy and we can do simulations. But the reaction mechanisms, we kind of, and there tend to be more than just one as well for many chemical reactions. So something that's very crazy that we study to this day is flame chemistry, how flames work and what things are made in combustion. So not even that is understood to a very large degree. But for a reaction mechanism, you have to look at this series of steps, much like Hess's law, if you remember that from earlier chapters. So, and knowing the rate law helps us understand the sequence of how things happen in a mechanism. Here's an example. Hydrogen plus 2 ICl makes 2 HCl's and iodine. The mechanism we're saying is that hydrogen reacts with ICl to make HCl and hydrogen iodide. Then hydrogen iodide reacts with ICl to make HCl and iodine gas. So we have 2 elementary steps, meaning they can't break down to simpler steps. So they interact directly in this matter without any other steps. And you can see that there is an intermediate here. You have hydrogen iodide as an intermediate. So hydrogen iodide is generated, but it's also consumed. So it's not in the overall reaction. So that hydrogen iodide is, like I said before, it's called an intermediate. There's other types of intermediates. You can have intermediates in terms of catalysis, like with enzymes or different types of things that happen on surfaces, but we'll talk about that later. This is also a homogeneous phase intermediate. So you have everything here is a gas, it's all the same phase. So the number of particles in an elementary step is known as its molecularity. So a unimolecular involves 1 particle, bimolecular involves 2, and they could be the same. So, and a termolecular involves 3. These are exceedingly rare. So usually it's either 1 or 2. And the laws for the elementary steps, each step is like its own little reaction. But the overall rate law must be determined experimentally. You can see that's you can't just look at something and say, oh, this is the way it's going to react. We can only tell this by experimentation. But the rate law of an elementary step can be deduced from the equation of the step. So the kinetics are decided by the slow step. And for instance, here are the different elementary steps. So A going to products, that's a 1 molecularity. A reacting with A going to products, that's a 2, and the rate law for this is Ka squared. A plus B goes to products, 2 molecularity, rate is K, A, concentration of A times concentration of B, and the rest of these are rare things. You can even have 4 collisions, but those are even more rare than 3 collisions. What is a rate law for the elementary step of Cl plus Co yields CClO? So it's going to be just the rate equals a rate constant times the concentration of Cl to the first power and Co also the first power. So it's just looking at the elementary step and then the rate law of those raised to their stoichiometric ratios as a power. And determining the rate step, what determines kinetic reactions is the rate determining step. It's the slowest step, and it tends to have the highest activation energy. And I always think of this, I think the textbook here goes in talking about a traffic situation. I think of it in terms of Thanksgiving dinner. So say that we're making 200 Thanksgiving dinners, and then we have enough time to make everything else. What's going to be the rate determining step in a Thanksgiving dinner? It's cooking the turkey, of course. That's the slow step. So when you plan out your Thanksgiving dinner, and if you're doing it for like 40 turkeys, you're like, all right, if I need to have a certain number of ovens to be able to do this. And making the other things is kind of easy. So making the cranberry sauce, making the mashed potatoes, these are pretty easy. The turkeys, cooking the turkeys, that's a slow step. That's what determines when dinner is served. So hopefully, or whatever, I hope I'm not offending anybody by talking about cooking turkeys for Thanksgiving dinner. Whatever, I mean that in a lighthearted sense. So whatever example, if turkey offends you, maybe tofu turkey or something of the sort. So another reaction mechanism. So we have nitrogen dioxide plus carbon monoxide makes nitrogen monoxide plus carbon dioxide. And we observe the rate to be a rate constant times the concentration of nitrogen dioxide second order. And so we can say, okay, this is a proposed reaction mechanism where you have a bimolecular reaction to form nitrogen trioxide plus nitrogen monoxide, a slow step, and the nitrogen trioxide is an intermediate form reacting with carbon monoxide, then to form nitrogen dioxide plus carbon dioxide. So you can see that a reactant is also generated back in this. So, but this is a proposed mechanism. Does this meet the overall reaction order? So, we can look for things with the with spectroscopy and whatnot. We can look for that NO3, for instance. So the first step is slower than the second step because the activation energy is larger. So if this reaction mechanism were to be true, looking at this graph here, you have on the y-axis you have potential energy, x-axis you have the reaction progress, and then going forward you have 2 transition states, and the first transition state is higher energy, so that's a slow step. So that's the one that's going to decide the chemical reaction. The kinetics of the chemical reaction is the first slow step. So to validate but not prove a mechanism, 2 conditions must be met. The elementary steps must sum to the overall reaction, and the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. These 2 things are important. And if you haven't guessed, it's much like we are making it up, because we are making it up. And nowadays we have more tools, but we also know it many times is much more complicated. So this is us trying to make sense of this. And we are getting better, but this is still something that we are working on. So some mechanisms have a fast initial step, and these have intermediates. And the first step reaches equilibrium very quickly. But then you can apply something, this is called the steady state approximation. So the intermediates reach a constant concentration. So that's the steady state approximation that the reaction is going forward at least where the intermediates are at a steady state. and then you have to include these into the rate law, and RDS is a rate determining step to get the rate law. An example of this here is this reaction, nitrogen monoxide going to dinitrogen dioxide being a fast step, and then you have hydrogen plus intermediate dinitrogen monoxide forming water and dinitrogen monoxide, and then hydrogen plus dinitrogen monoxide make water and nitrogen, and then 2 hydrogen plus 2 nitrogen monoxides makes 2 waters and nitrogen. So you can see here we have 2 intermediates, one being dinitrogen dioxide and also dinitrogen monoxide. These are 2 intermediates, and you can apply the steady state approximation such that, well, the rate is going to be the slow step. It's the elementary reaction slow step. So you have rate is equal to some rate constant times the concentration of hydrogen times the concentration of dinitrogen dioxide. But what is the concentration of dinitrogen dioxide? Well, we have the top reaction here. We have the rate forward and the rate reverse the same, meaning that the rate forward is the rate equals K1 times concentration of NO squared for the second, and the reverse rate is equal to K minus 1 is, I'm sorry, the rate backwards is K minus 1 times concentration of N2O2 to the first power. So you set these equal to each other. Those 2 rates forward equals the reverse rate, and now we got the concentration of dinitrogen dioxide. We have the concentration of the intermediate using the steady state approximation. Then we can plug that back into the observed rate. I'm sorry, we can plug that back into the rate law for step 2, and then we get this rate being K2 times K1 over K minus 1, and the minus 1 just means the opposite direction for step 1, times hydrogen times nitrogen dioxide squared. So catalysts, these are substances that affect the chemical reaction and are not consumed in the process. They can be altered, but they are always regenerated. And these work by offering different pathways that lower the activation energy. And they are, like I said, they can be consumed, but they are always regenerated. Overall, they're not consumed. And so, for instance, ozone plus oxygen, well, oxygen radical makes 2 diatomic oxygens, but including chlorine in the gaseous phase, this can create the ClO intermediate, and this proceeds at a faster rate. And you can see this is a homogeneous, so same phase, homogeneous catalyst. So ClO is generated, but it's also consumed, and the catalyst is then generated again. It can go on, and then it could break apart more ozone. So looking at a chemical reaction here, y-axis is still potential energy, x-axis is reaction progress. The problem with well, good thing, it's a problem because ozone depletion is not something that's desirable, but the transition states are decreased for a catalyzed pathway. It's easier for the reactions to get the products. So a heterogeneous catalysis, these are different. So, this is backwards. The heterogeneous catalysis are in a different phase of the particle, and the homogeneous particles are in the same phase. So of the two, the heterogeneous catalysis are the more powerful ones. An example of that is a catalytic converter. You have platinum or palladium nanoparticles on a zeolite substrate, and then the reactants go in, the carbon monoxide, unburned hydrocarbons, and nitrogen oxides, and then these react to form nitrogen, water, and carbon dioxide out of the car. So types of catalysts, homogeneous catalysts are the same phase, and heterogeneous catalysis, these are different phases. So I mean, like, solid, in this case, gas and solid for the heterogeneous catalysis. And ozone, unfortunately, ozone depletion turns out to be heterogeneous catalysis. So it can be both. It can be homogeneous halides. It can also be on the surface of ice crystals or volcanic ash. You can have heterogeneous catalysis of ozone destruction. So how does heterogeneous catalysis work? Depends on the chemical reaction, but for instance, you can have molecules absorb. You can have physiabsorb and chemabsorb. So the hydrogens, they're chemabsorbing. They're breaking apart chemically. The ethene looks like it's physiabsorption. It's not really changing its structure. But then the reaction takes place on the middle surface, and then the product can leave. Enzymes, these are biological catalysts. These are big, clunky molecules, usually proteins. Proteins are almost exclusively, or enzymes are almost exclusively proteins. So they think of it as this big, clunky molecule that grabs onto another molecule and holds it steady. And many biological reactions are optically active, so they're very, very, very site-specific. So enzymes are very site-specific. And the way that they work, the enzyme reacts with the reactant or substrate to form an enzyme substrate, and then the enzyme substrate will react with an enzyme to form the product, and that's the slow step. And you can have two enzyme substrates form and then react, or you can have one enzyme substrate form and then it reacts, like breaking things apart, like breaking apart sucrose, for instance, is an enzyme with just a single enzyme substrate. So, for instance, here you have the substrate that fits over the enzyme, and then if it's like the breaking apart of sucrose into glucose and fructose, that can be done easily on an enzyme. So, this one is hydrolysis of sucrose. Yeah, so it breaks it apart. So this is an example of one. There, it's that. And the binding, well, it has to the enzyme substrate. So the substrate has to fit on the enzyme in a certain way, which also tells you about enzymes. If the shape is off, it doesn't work anymore, and that's also known as denaturation. So when an enzyme is denatured, it no longer works. So, which you can cover in more classes. So, thank you for listening, and goodbye for now.